Assalamualaikum and very good mornings to all of you. First of all, I would like to introduce myself. My name is Mohd Sofwan Mohd Resali. I'm a senior lecturer at University Malaysia Perlis, UNIMAP. Before I start my presentation for today, I would like to thanks to Professor IR TS Dr. Muhammad Rizal bin Arshad, President of Malaysian Society for Automatic Control Engineer, or MACE, and also thanks to the organizer from Malaysian Society for Automatic Control Engineer for inviting me to give a talk for today. Uh, uh, of Today in Facebook of Malaysian Society for Automatic Control Engineers. Thanks again. Okay, today my topic is about vibration-based energy harvesting application, a self-powered wireless condition monitoring system. Before that, my background basically, I'm graduated from University Science Malaysia in Bachelor of Electric and Electronic Engineering. And after that, I'm further my study in a Master in Mechanical Engineering from University Tenaga Nasional, Unit 10. Basically, my research topic during master study is on vibration-based energy harvesting system. And then after that, I complete my PhD study also from University Tenaga Nasional, Unit 10, in energy harvesting, vibration-based for wireless condition monitoring system. Okay, today this is my topics, vibration-based energy harvesting application, a self-powered wireless condition monitoring system. Okay, before that, this is my contents for today's presentations. First of all, I would like to give an explanation on the introduction to energy harvesting, and then key trends driving innovations, the economics behind energy harvesting, how does energy harvesting work, source of energy, and then after that, I will touch on the vibration-based energy harvesting design consideration guideline, the application, and then conclusions. Okay, what is energy harvesting? Energy harvesting, or also known as a power harvesting or energy scavenging, is the process in which energy is captured from a variety of ambient energy sources and converted into usable electric power. Okay, the most important things when we talk about energy harvesting, it provides a very small amount of power for low energy electronics. When we talk about low energy electronics, the power output from the energy harvester or for the application of electronic is between microwatt and milliwatts. Okay, energy harvesting allows electronic to operate where there's no conventional power source, like a battery or from the electrical connections, eliminating the need of wires or replacement of batteries. Okay, energy harvesting system generally includes circuitry to charge an energy storage cell and manage the power, providing regulation and protections. Energy harvesting powered system need reliable energy generation, storage, and delivery. That's why in energy harvesting must have energy storage as a energy harvested transducer. Energy sources is not always available, like solar at night power, and then let's say for motor vibration at rest. Okay, energy harvesting can provide endless energy for the for the electronics lifespans. In many cases, energy harvesting can eliminate battery from wireless devices. Okay, ideal for substituting for batteries that are impractical, costly, or dangerous to replace. Okay, what's the energy harvesting? As shown in this figure, a small amount of energy around us, maybe from car engine, uh, um, from car engine, from walking, from train, and so on. And then we converted to electric energy by using energy harvester like a piezoelectric or electric for the thermo, or for solar panel or radio wave, and then thermo electricity. And then the application is to the electronic device like watch and so on. Okay, so this is the big picture of the energy harvesting. We have energy harvester here, let's say from piezoelectrics, and then we need to convert. Let's say in the case of piezoelectric, it produces AC voltage. We need to rectify to the DC, and then store in the energy storage, and then have some electronics switching circuits, and then after that, the power capture will flow to the load electronics applications. Okay, why energy harvesting? First, transducer are getting more advanced. Okay, transducer are the device that turn one from the energy into another. Steady advances in transducer technology, especially recent breakthroughs in material and semiconductor, have made a new type available and increased the efficiency of all of them. Okay, low power circuits use even less power. Just as the power available from transducer have been increasing, the power needed to run electronic circuit has been decreased. Power improvement do not totally depend on semiconductor advance. Power consumption has become a major concern with larger chips that motivated circuit designer to develop low power design for digital and analog circuits. The improvement made for large chips are being carried over to smaller circuits, resulting in device that can be powered entirely from harvested energy. And then the IoT is driving devices closer to the edge. This is the applications. The Internet of Things, IoT, is here and expanding rapidly. Depending on which analysis you refer to, predictions of connected things range from 20 billion to 50 billion in 3 years. Our computers, smartphones, and web servers are already connected. So the next connectivity wave will focus on the devices. Okay, this is why we need for the energy harvesting. Okay, electronic costs are coming down faster than battery costs. The price of electronics is so low. If a battery is needed, it can represent a major fraction of the cost of the device's cost. This is a major reason behind the move to device relying on energy harvesting for power. Battery technology has no cap pace, so module that requires battery may not satisfy a design requirement because module would be too large. One possibility for in addressing the reliability, management, and size issue associated with batteries is to remove them altogether. Energy harvesting is making this possibility a reality. Okay, devices number five. The devices are only as reliable as their power source. As wireless devices are deployed in large number and users are discovering that battery reliability is not usually up to the task. A typical goal for the low power networking protocol described above is often a 10-year battery life on a single coin cell. Several approaches are claiming success. This estimate often rely on simple calculation that compare steady-state power consumption to battery capacity specification. Real-world deployments, however, often show unacceptable failure rates. Okay, the problem is that battery lifetime is multi-dimensional problem. Battery reliability begins with the manufacturing process. Unlike electronic components that have easy to predict lifetimes, battery are based on chemical processes that have many different failure modes. Even manufacturers who need out infant mortalities still have field failure, and the unavailability of data makes it impossible to include those failure in models and calculations. Okay. The second topic is on the key trends driving innovations. New innovative products are smarter, smaller, and wireless. If we refer to this figure, now most of the electronic manufacturer start producing very efficiencies electronics devices which have ultra power ultra power of um, ultra power processors and electronics. And then we have smart devices and sensors for by using very low power as an input power, and then integration with other components uh, like in this figure, a very small one, and then eco-friendly and renewable energy. Okay, new innovative product are smarter, smaller, and wireless. Smart device that must communicate status or control. There will be billions of new network smart devices. Okay, the application on the health, industrial, buildings, appliance, and transportation, and so on. Okay, new power solution are required. Okay, this is one of the examples for this product from ST Electronics. They produce the ultra power platform, which is need only 1.65 volt to 3.6 volt power supply, and then just 9 microampere low power run mode. Okay, and then just 1.5 watts. Okay. And then the key trend driving innovation now also um, uh, some manufacturer, or I think many manufacturer now producing for the, let's say, for the wire for the power for the or wireless system, low power microprocessor with nano amp sleep current, low power radio transceiver, and then have energy efficient radio protocols by using let's say Zigbee, Bluetooth, ENT, and then micro power sensor with low sleep currents, and then lower quiescent current preferred circuits. Okay, this is what the key trend driving the innovation. Why we go depth into the research on study on the energy harvesting. We hear also, let's say, billions of smart devices deployed over the next 10 years need powered autonomously and be off-grid, have a power source that lasts the life of the device, be small, integrated, and cost-effective. Okay, if you can see here, if we can see here now for the energy harvesting power range for WSN, which is a wireless sensor node. Okay, this is the energy harvesting sweet spot. So now the technology is start work at the very low power input. So let's say for the Bluetooth now, maybe around more than just 10 milliwatts, and then hearing aid wireless sensor just need for 1 milliwatt to power up, and the sensor 100 microwatt, RFID tag only 10 microwatt, and then watch or calculator 1 microwatt. Okay, this is another thing is when we talk about energy harvesting, we aim try to eliminate the conventional energy storage like battery. So this is the comparison between lithium ion battery, thin film battery, and supercapacitor. Okay, in terms of recharge cycles, supercapacitor have more advantage compared to the lithium-ion battery and then thin film battery. So that's why most of the now when people who work with the energy harvesting for the low power applications, for the energy storage, most of the researcher are using supercapacitor as an energy storage. Okay, then this is what's the trend now? Uh, portable. We have a portable electronic devices, portable electronics equipment, which is used by using batteries. But that's why we need to come with another alternative of source of energy harvesting. Okay, the economics behind energy harvesting, if we can see in this figure, energy harvesting market in 2012, the business is the market is around 0.7 billion dollar, and then it increasing by 2017 by with 1.5 billion dollar. Okay, if you can see here, the big consumers on the electronics, we have 130 millions, and then healthcare, wristwatch, laptops, mobile phones, wireless mesh, and military. So they have a big market or big potential for energy harvesting in the future. Okay, this is okay. The energy harvester market forecast also, we can see here, it increasing from year to year from 2014 to 2018, which is we have here four types of energy harvester: piezoelectrics, thermoelectric, photovoltaic, and electrodynamics. Okay, this is four key design consideration for energy harvester. First of all, we need to determine energy available from our environment. Let's say solar, is it uh, is it available for the light? Let's say for indoor solar, and then thermoelectric, or vibrations, or temperature. Okay, and then harvest energy as efficient and cost effectively as possible. Okay, this is designed for maximum peak power point and avoid component with excessive leakage of quiescent current. Basically, this is most of for the points number two. The key number two is basically it's referred to the power management circuits, and then calculate application power requirements in all operation modes and minimize to the fit available input power energy harvester. Okay, this is about the applications. We need to calculate first, or we do we call it power budget for our application, like sensors or microcontrollers or radio frequency. Okay, and then number four is size of storage for time when ambient energy is not available. So this is from the power budget at the point number three. Uh, we can calculate the size of a storage. Let's say for the if you want to use a supercapacitor from the power budget, we can calculate what's the size of supercapacitor so that it can match with the power available from the energy harvester. Okay, how does energy harvesting works? An energy harvester comprise one or more transducer, power conditioning, and energy storage. Okay, this is energy harvester. This is a power conditioning, and then is the energy storage. These technologies work together to collect energy and they will deliver power to the device. On the other hand, the device which use the energy needs to be designed to work with energy harvesting as the power source. Okay, transducer. What is the function of transducer? The transducer is to convert energy from one energy type to another energy type, usually electrical. Okay, like vibration, we convert by using piezoelectric as a energy harvester, or we call it a transducer, to convert from the mechanical vibration to the useful electrical energy. Okay, power conditioning is necessary because the natural output of the transducer can be intermittent, and the wrong frequency, voltage, and current to directly drive the device. As a specialized DC-DC converter, microchip takes in power from the transducer and convert to voltage, which can then be stored or used. Okay, energy storage is needed to balance the energy supply and energy demand for application where energy is used as soon as it is collected. No storage is needed. Okay, usually, however, a rechargeable battery, capacitor, or supercapacitor is used. Batteries degrade over time, and so the lifetime of the storage device can often be the limiting factor in the overall lifetime of the harvester. Okay, if you can see here, just go through for on this figure. Okay, this is a transducer, or we call energy harvester, and then it produce electrical from the mechanical to the electrical. So this is electrical energy. We need to rectify whether we use a AC/DC or DC to DC converter. Let's say because when we have a power conditioning circuit here, let's say most of the voltage input, so the electronics, let's say most of them work at a 5 volt, but our harvester produce let's say 16 volt, so we need to step down the electrical energy. So and then okay, before that, let's say if piezoelectric produce AC voltage, we need to convert to the DC voltage, and then after that, we step down to the 5 volt to match with the operating voltage of electronic device. Okay, source of energy. For this is example of ambient energy, ambient energy that we can harvest by using energy harvesting. Okay, light captured by photovoltaic cells. This is very well known in solar. Vibration or pressure captured by a piezoelectric elements, or we have electromagnetic or electrostatic. Okay, we have a vibration and temperature differential by using a thermoelectric generator, and electromagnetic and radio frequency. So this is to harvest from the RF. Okay, this is energy harvesting transducer. What ambient energy is available? Okay, this is for energy source. This is basically when we focus, when we talk about energy harvesting for ambient, we focus on the low power. Okay, this is the typical power output by using small solar panel, solar cell. Okay, from can harvest normally 10 microwatt to 15 milliwatt. And then for the vibration, normally we use, this is piezoelectric, and normally the typical output power is from 1 microwatt to 20 milliwatts. And this is thermal, normally from 0.5 milliwatt to 10 milliwatt. and then RF depend on the wide range. Okay, just for the introduction, light energy, this source can be divided into two categories of energy: indoor room light and outdoor sunlight energy. Light energy can be captured via photosensor, photodiodes, or solar photovoltaic panels. Mechanical energy, vibration from machines, mechanical stress, strain from high pressure motors, manufacturing machine, and waste rotation can be captured and used as ambient mechanical energy sources. Thermal energy, waste heat energy, variations from furnace, heaters, and friction source. Electromagnetic energy from inductors, coils, and transformer can be considered as ambient energy sources depending on how much energy is needed for the applications. Human body, we can use mechanical or thermal heat variation. Energy can be generated from a human or animal body by action such as walking and running. Natural energy like wind, water flow, ocean wave, solar energy can provide limitless energy availability from the environment. Okay, this is the block diagram of a general ambient energy harvesting system. Okay, this the first row shows the energy harvesting sources like electromagnetic, piezoelectric, electrostatic, thermoelectric, and solar energy. This is we can harvest from waste mechanical, mechanical energy, and then charge varactor, electrostatic, thermopiles, and photovoltaic cells. This is what's the transducer. Okay, and then the row number 3 is the third row, show the energy harvesting technique from each source. For the electromagnetic, a magnetic field, and a convert. And then we have our, for this row, we have energy harvesting and battery charging circuit. Okay, by magnetic fields, the electromagnetic can convert, let's say, from the waste mechanical to the useful electric energy. Okay, for piezoelectric, by straining, deforming, and vibration of piezoelectric materials. Electrostatic also for vibrations. And then for thermoelectric, temperature differentials between opposite segment. And then for the light interface with heavily doped narrow and region. Okay. So I just finished on the little bit of introduction of the general about energy harvesting. So now I will go focus on the vibration-based energy harvesting, or we just form on the VEH. Okay, mechanical energy sources, steady-state mechanical source like wind, flow, current. This is steady state, which is, let's say, wind of flow or current from the wave can produce a steady state mechanical source which that can produce vibration. And then intermittent mechanical source like human activity, walking, running, or vehicle passings on the bridge. Vibrations energy depends on the amplitude and its frequency, mass of harvesting device relative to the vibrating mass. Okay. We have normally in vibration-based energy harvesting, we have 3 types of energy harvester or transducer. Most people we use piezoelectric conversions, electrostatic conversion, and electromagnetic conversions. Why people widely use on the piezoelectric? Because the output power, if comparing to between these 3 transducer, piezoelectric normally produce power power output is more higher the highest one if compared to the electrostatic and electromagnetic. Okay, from this is this as example, we have a piezoelectric, and then we attach to the shaker. We have holder, and then MACE at the end of the tips of the piezoelectrics, and then this is uh, uh, sk- uh, 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 this is the diagram if we for the motion equation of the piezoelectric. Okay, we have a motion equation below. Describe the generic mechanical to electrical conversion model. Okay, so where M here is the mass, Y is input displacement, and then Z is spring deflections, D is damping coefficient, and K is spring constants. Okay, this is if we can see here on in this graph, this is power dissipations, and then we have on the frequency. Okay, omega here is vibration frequency, and then omega n is natural frequency. When the vibration frequency is matched with the natural frequency, it produces the peak power resonance here. We can see here. And then this is the how we calculate on the power output of the electric energy from the vibrations. Okay, zeta t is a damping factor here. Okay, if we increase the damping factor, it will reduce the peak power, but it will increase the bandwidth here. If you can see here, let's say if we decrease the damping factor, the factor is decreased. The peak, if you can see this on this line, when the factor is decreased, the power, the peak power also decreased, but the bandwidth is increased. If compared to the if the damping factor of this line is increased. Okay, that's fixed frequency. We have low damping factor. And then if we want our design on work on the various frequency, we can decrease the damping factor, and then we have a high bandwidth here. Okay, this this is a vibration-based energy harvesting design consideration guideline. First, when we want to design for the vibration-based energy harvesting uh, 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 when we want to design for the energy harvesting vibration-based energy harvesting system. This is based on my experience. This is the consideration guideline. First, we need to identify the input of vibration. Normally, it means let's say if you want where you want to implement this vibration based energy harvesting. Let's say I have example on this slide. In this slide, I have an example. Let's say for me, for my case, I want to harvest energy from the uh, on the vibrating cooling fan at the one of the power plants in Malaysia. So I need to identify what's the input vibration, what's the vibration input at the vibrating motor there. Let's say I need to identify first is the frequency, and then the number two is the accelerations. Because of frequency and acceleration, it will give because we will need to mesh for the harvester itself of frequency, need to match with the input vibration frequency. Okay, this is a working frequency, and then number two is working frequency versus input frequency. Input frequency is, let's say, the vibration motor. Working frequency basically it refer to the our energy harvester itself. Let's say in my case, piezoelectric, I need to make sure that working frequency of my piezoelectric is same with the input frequency of the vibrating motor at the power plant. Okay, and then we need to measure the optimal output power of the vibration-based energy harvester. And then number two is power management circuit. We need to consider on the control circuits. And then identify total power budget. Basically, we need to identify what's application we want. So let's say on my case, I need to power up for the autonomous system, for the wireless autonomous system. I need to power up sensors, microcontrollers, and the RF module. So I need to identify what's the total power budget there of the overall system. And then from the total power budget, I can identify such as size of a supercapacitor. Okay, let's say the total budget for the overall system, I calculate, let's say it's 2 milliwatt. So from the calculation, my size of the supercapacitor is 2200 microfarad. Okay, and then finally, the total power losses can be reduced by reducing the number of devices inside the power management circuit. Okay, the most important thing in power management circuit also, we need to design the circuit is as simple as we can, because to reduce the power losses and so on. Okay, this is the methodology. Okay, first of all, field measurement of vibration level, field experiment estimation, field vibration input. Okay, the other output here, we know what's the working frequency of the vibrating motor, and then characterize a basic piezoelectric energy harvester. Okay, let's say for my case, I using piezoelectric from that we bought from the piezo system, and then we need to identify what's the characteristic of the piezo. Is it mesh with our requirement of the input frequency? And then let's say for the step two, we identify the working frequency of the piezoelectric that we bought, we use from piezo system is not meshed with the input frequency. So we need to do some strategy to improve performance of energy harvester. Okay, let's say in my case, I'm using extension beam, and then put some latex rubber, and then electromagnetic harvester, which is for this system I'm using a hybrid system. The harvester is hybrid combination of piezoelectric with structural modifications and also electromagnetic energy harvester. Okay, and then after that, on the power management circuits and electronic load, and after that, performance testing of wireless condition monitoring system. Is it this performance testing is conducted at the laboratory test and field test. Okay, this is field vibration input. This is a vibrating cooling fan. This is a motor of a cooling fan in one of the power plants in Malaysia. So from there, we identify that the frequency that that vibrate the motor is 48 hertz, 50 hertz, 52 hertz, and 57 hertz. This frequency is basically on the different spot of the sensor we put to measure the vibration. Some let's say for 48 hertz, we identify this is the point, and then let's say for 50 hertz, maybe at this point, and 52 at another motor. But the overall, that machine is vibrating at 48 hertz, 50 hertz, 52 hertz, and 57 hertz. So that's why to make sure that my energy harvester, in my case, I'm using piezoelectric, need to the working frequency of the piezoelectric need to operate at this frequency. Okay, this is the first one is the field vibration input. So this is one is I have three types of piezoelectric. So this one is the original piezoelectric that we use from piezo system. So from this from our simulation and experimental, so it shows the resonant frequency of this, or working frequency of this piezoelectric, is 80 hertz, which is not didn't match, is quite far to match to match with the input vibration frequency here. So we need to strategize how to make sure our piezoelectric can work by within this range of frequency. Okay, from for the figure number 2, I just mentioned here in PZTME. Basically, I connected with the extension beam here using PTFE beam, and then the working frequency now I can decrease to 50 hertz as to match with this input of frequency. And then the last one is basically I put on the latex rubber around the piezoelectric, basically just basically to prevent this when it vibrate at a certain frequency, or maybe suddenly at the different acceleration of the vibration. Basically is to try to avoid this piezoelectric is broken. But anyhow, from experiments and simulation, the resonant frequency is 48 hertz, still mesh with this range of frequency. And then the power output is quite higher compared to the extension beam and without extension beam. Okay, this is the energy harvester. Okay, and then the second harvester is on the electromagnetic. Basically, this is the electromagnetic coil used here, and then I'm using a magnet as a mesh for the piezoelectric beam here. Uh, First, it functions as a mesh, and then second thing is when it moving up and down, it will produce the electromagnetic flux here, and then produce electrical energy. Okay, if you can see here, this is the result. And then the last one is when I using as a hybrid system by a combination of piezoelectrics with extension beam, and then surrounded by latex rubber together with the electromagnetic coil here, and then the result is uh, uh, 3.61 is quite higher compared to the without without a hybrid system. So the hybrid system you basically producing more output power compared to the standalone system. Okay, this is the power management circuit. Basically, I have a hybrid system here, PZT and electromagnetic coil, and then I have a AC/DC rectifier here. Okay, for the AC/DC rectifier, this is the so that I'm study basically on the series connection of the AC/DC or in parallel. Okay, if you can see here, or single connection, it mean one by one AC/DC separate AC/DC rectifier. For this one, combination in series for the AC/DC, and then this is a combination of in parallel. Okay, uh, in terms of this is the characteristic that I need to compare. Okay, for the circuit complexity, if using a single connection, it's more complex compared to the series and parallel. Small size circuits, of course, need more space, and then charging time to fully charge at the storage circuit here need is very slow. Slow and very slow is more faster. Okay, in terms of power, by using a parallel connection of AC/DC, parallel produce more higher output power and efficiencies if compared to the single connection and series connections. Okay, for the power management circuit, I have a AC/DC rectifier, energy storage circuit, switching circuit, and DC/DC converter, and electronic loads. Basically, switching circuit here is function to avoid energy stored in the supercapacitor flow all the time to the DC/DC converter, so that it will to prevent. Basically, in this power management circuit, my design is when it fully charged, then the switching circuit starts to turn on and then flow the energy to the DC/DC converter. Okay, for this DC converter, because if you can see here, it produced around 17.8 volt from the piezoelectrics here. So, but the electronic load here, let's say sensor, microprocessor, and then RF module here, the voltage, the operating voltage is 5 volts. So I need to step down by using DC/DC converter here from 17 volt to the 5 volt. Okay, this is power budget. This is the voltage and then for the wireless devices that I use in for the applications. So this is the power management circuit. Basically, VLOAD here is the input DC from harvester from AC/DC. So this is the VLOAD here, and then we have C1, C2, C3 basically to smooth the signal of the DC voltage, and then here this is control circuit. Here this is gate, and then this is a super capacitor. So the energy produced from the energy harvester go inside here and then stored in C out. C out basically is a super capacitor, and then V out is connect to the DC/DC converter. Okay, this is my power management circuit. The harvester frequency range is from 48 to 52 Hz. The input voltage basically can 8.2 to 100 volt AC. Time for initial supercapacitor charge time in laboratory test, we test it take 130 seconds, and then if in field test 90 seconds. Why? Because in this laboratory test, we fix the frequency and also fix the acceleration. We avoid not to exceed at the 0.25 G, because let's say if we exceed at 0.25 G, basically at the normal condition, it will broken down the motor. But because why 90 seconds in field test? Basically, when we test at the uh, real vibrating motor, we cannot control the acceleration there. Maybe sometimes the acceleration there is more higher compared to the 0.25 G acceleration. Okay, the power input here is 3.61 megawatt, milliwatt at 48 hertz, and then the power output is 2.97 milliwatts, and then the efficiency is 82.2 percent. The power losses is 0.25 milliwatt. Basically, 0.25 milliwatt is losses between start from the AC/DC until to the DC converter. Okay, output voltage DC is 5 volt. Okay, operating system hybrid energy harvester from electromagnetic and piezoelectric standalone system powered by only by harvester. No need for the external source like a batteries. Single supply voltage, small size, and AC/DC full bridge rectifier circuits. Okay, if you can see here, this is what we test in lab. We have a sensor here, and then it is shaker. And then inside this board, we have a controller module like a microcontroller, AC/DC rectifier, and also for the storage circuit. And then this is the phone that when it start vibrate, we will monitor the signals of data from the sensor here. Okay, this is how we test inside a lab. We have a PC here and the function generator, amplifier, shaker, multimeter, and then function generator. Okay, this is basically this is a laser vibrometer here. This is a laser vibrometer module. Laser emitter will control it will control the frequency here. Let's say it will read what's the frequency and acceleration, and then we can monitor here. So let's say we want to 48 hertz at 0.25 G. We will monitor at this function generator and the amplifier. So okay, this is how we test in field test. We have this is chiller room also, and then we put the sensor and energy harvester here, and then here is the power management circuit. And after it starts produce electric energy and there's have enough power, it will start to power up the sensors, and then the data is sent wireless through Bluetooth system to the Android phone. So if we can see here, this is the XYZ. This is the data of accelerometer sensor, and then we have a temperature sensor here. Okay, same also. That's this is another system of wireless condition monitoring. This is we test on the lab test and also in the field test. This is we test in at the one of the power station in Malaysia. Okay, I want to share with some video with all of you. Okay, let's get this one. I can show you. Okay, in this video, this is our energy harvester. We have piezoelectric here, combination with electromagnetic. And then we have here we have a power management circuits, storage circuit, and then DC-DC converter, and then the power is power up connected to the RF module with the sensors here. Basically, this multimeter, we want to measure the storage power of the supercapacitor. So that system, we transmit the data of acceleration and under temperature to this laptop, if you can see here. Okay. Okay, this is how we conduct experiments in laboratory. Basically, this is we using LabVIEW software to, and then here we put the input of what frequency we need and the accelerations. If you can see here, this is the voltage uh, that's stored inside the supercapacitor. So this is the piezoelectrics with a different mass. This is power management circuit. This is a supercapacitor. Basically, this is the AC/DC rectifier here, and then we have this is a full bridge AC/DC rectifier here. Okay, basically this is the input, the signal that we read from accelerometer sensor and then temperature sensor. Okay, okay, I think this is that I can share with you. Okay, this is the result and analysis. If you can see here from this graph, this basically this is a voltage of the electromagnetic energy harvester, and then okay, this is for the blue one is the voltage from voltage output of the electromagnetic energy harvester. Okay, this is only piezoelectric standalone, and then this one is the hybrid together from the piezoelectric and electromagnetic. This is the output voltage. Okay, from this graph also, let's say we can see here after 100 and if we can see here this is basically voltage at capacitor. This means by using hybrid energy harvester combination of piezoelectric and electromagnetic, the time taken to supercapacitor is fully charged is shorter, faster compared to the if we use only piezoelectric. Okay, and then this is the 5 volt. Basically, it refer to the output voltage at the end of the power management circuits. Okay, for this graph was for the graph basically it shows for the blue one is the time taken to the supercapacitor to fully charge, and then when it start to fully charge, it will start to power up all the electronic applications, electronic devices. If you can see here, it produce 5 volt, and then now off when this electronic load off, supercapacitor start to charging, and then when it fully charged, it will start to the power on to power up the electronic device at the 5 volt. So this is the graph. Okay, for this system, for the vibration-based energy harvesting system for wireless condition monitoring system, this is the specifications. Operating system, operating of frequency is from 48 to 52 hertz. Input frequency from 8.2 to 100 volt. And then for time for initial supercapacitor charge time is 130 seconds in laboratory test, and then 90 seconds is at the field test. The input power is 3.5 milliwatts. Output power is 2.97 milliwatts. The efficiency is 85%. So the operating system is a hybrid energy harvester, standalone system, single supply voltage, no need for the external batteries. And then small scale size and AC/DC full bridge rectifier circuits. Okay, conclusions. The size of the vibration energy harvester can be reduced by exploring the design and fabricate using MEMS technology. Now, even for the vibration energy harvester, people start to explore on the MEMS technology. Okay, the application of the vibration energy harvesting should be comprehensive, not only harvesting from energy from vibration on the machine, vibrating machine, but vibration also can come from the movement of water flow from underwater. Okay, a research study not only focus on the optimum design or tuning the design of the harvester, but must look in deep on the optimization of the electronic load application device and power management circuits design, and could significantly improve the overall power performance system. Basically, we will talk on the power change. Is it start from the harvester itself, power management, and also for the electronics application itself. So we need to consider all of these three power chains, not only on the harvester, but also on the power management and also for the electronic applications. I think that's all from me. So I hope that my presentation today, it will benefit to you and also to me. And thank you very much to all of you to spend your time to listen to my presentation today. I'm sorry if my presentation today is not meet your expectations. Hopefully that after this we can meet again at the different platform and times to times. Okay, that's all from me. Thank you very much, and I hope that we can explore more on basically on the energy harvesting or renewable energy or any field of your research study. Thank you very much. Assalamualaikum, and thank you. See you again.